So I'm very happy to have Lesia Semenova here with us. She's a postdoc at Microsoft Research in New York. She completed her PhD in the Duke University, and she's interested in interpretability and responsibility and trustworthy and AI. I'm personally lucky to work with her, to collaborate with her, and it's a real pleasure. And today, we are going to hear about one of our works on about how to do simple and accurate model. So the floor is yours, Lesia.
Thank you so much, Michael, for the introduction. And so overall, my research revolves around, like, I call it as there are two hats. You have practical one and more theoretical one. So today I would like to talk about a little bit more theoretical aspect of interpretability or simplicity of my work. And the talk is called on the existence of simple yet accurate machine learning models. And before we jump into a little bit more results, let me give you actually an example of a simpler or interpretable model. And this tree was constructed while I was collaborating with immunologists. We were provided a data set from people who got infected with, who had HIV, and it came from Duke and University of Chapel Hill hospitals. And the goal was actually to understand something which is called viral reservoir. It occurs when people undergoing treatment, but still some virus persists in their body in the latent state. And it's really important to understand this reservoir in order to find like what's going on with the immune system and possibility to find cure. So anyhow, we were given this data set and it had like 138 different features of demographics and immunophenotypes information. And here is a sparse decision trees that we optimized for accuracy and interpretability and sparsity. And it has only 5 of those features and it's 82% accurate. And this is an example of what I call an like interpretable model and quite simple one. It was useful for domain experts to also try to find some patterns. Like for example, as I can just take some leaf and follow it back to the root, backtrack progress and see what's going on and how decisions are made. And just an example that is not only trees, here is an example of scoring system. And in this case, the goal was to predict mortality of the patients. And it's also really easy to read and it easily fits on this specific slide. So for example, if all of the measurements of patients are in order, just temperature is out of order, let's say it's like very, very low. So we see score 23. Then we go back to this scorecard and check like, oh, score is 23. So here is my risk of mortality. So again, it's really easy to understand how this model makes its prediction. It was also optimized for both accuracy and sparsity. And both of these models are interpretable. And I think there are enormous benefits from having interpretable models for multiple reasons. And let me just name a few of them. So one, it helps to identify and mitigate potential biases. For example, that's what happened with Glenn Rodriguez, where he was subjected to extra year of jail because of clerical error. If interpretable model would be used, it would be just easier to see that error instead of black box. It also are easier to troubleshoot. So, for example, medical imaging, there is an FDA-approved algorithm for detecting bleeding in brain, and it fails, and nobody knows why. And the researchers who developed this algorithm also spent like countless hours trying to find what's the reason for its failures. And then they said, okay, we give up. We don't know. So I'm not saying that with interpretable models, they would be able to answer this question, but at least their debugging process would be way easier to see. Also, interpretable models can provide you truthful and complete explanations. For example, under current law to explain the decisions made by different systems, let's say some explanation was provided, and then the customer, for example, he was denied of loan, go back home and within some time was able to improve that reason and come back and deny it again, but for different reason. So this would not happen if one interpretable model was used and whole chain of thought provided to the customer so they could see like complete explanation for what's happening and why they're being denied. On top of it, interpretable models can help to enable trust into the system. I want to be really careful here not to say equal trust, because you can still see problems and you can distrust the system, but at least this trust is enabled. And they also facilitate a lot of interactions with domain expert, as for example, for the HIV trees that I presented at the beginning, we had a lot of discussions about like what this immunophenotype mean and how it corresponds to related literature and how it corresponds to already existing biases in that specific domain. So there seems to be an enormous number of benefits from using interpretable models. So why then we don't do it? And there could be multiple reasons for that. So for example, it could be somebody's personal preference. Let's say that I'm really comfortable working with gradient boosted trees. I worked with them for a long time. They work well for tabular data set. I like it, and it's just my preference. There is nothing I can do in this case, right? Could also be this belief in difficulty of designing these interpretability constraints and optimizing for them. And it is indeed a legitimate question. However, there have been a lot of research in this area, including the scoring system and sparse decision trees that I showed at the beginning. On top of it, there also has been work in interpretable neural nets, whereas they've been optimized either to widen the latent space, either to do case-based reasoning, where based on some input, we can reason why the model made this decision, this specific decision. So there is progress in that direction as well. I believe the reason why we don't use models more often is also rely on this belief that has been in the community for a long time, that there is an accuracy interpretability trade-off. And the trade-off is specifically like this. If we plot on x-axis simplicity or interpretability, and on y-axis accuracy, and then we run different data science algorithms such as gradient boosted, random forest, linear models, we will see a cutoff where we will look at more complex models, and they will be low in simplicity and high in accuracy. And then we'll take more simple models, they will be high in interpretability and low in accuracy. So what we're going to do today, we're going to see that for a lot of high-stakes decision domains and data sets in these domains, this belief is actually wrong. And for a lot of these data sets, a little bit different picture is happening, which is there exists this optimal sparse model that achieves the same error rate as other black box models. I have to be honest, this may not be the first linear model you come across. You will need to specifically search for it and optimize, and by itself, it may be a complex combinatorial optimization or some other type of optimization problem. But the point is a little bit different today. We would like to talk about some theoretical notions and properties of data sets, such that we can think about, oh, I think in this case, this model is very likely to exist. So now I'm going to go and spend a lot of my time in order to try to find it for my specific problem, because the benefits will be high. More specifically, we will go through two different steps. First one, we will talk about a set of good models. And this is a set which I also call Rashomon set, where you have multiple models that perform approximately equally well. And we will chat about how it relates to existence of simple rate accurate models. And the second step, we will talk about a little bit properties of the data, and more specifically noise in our data generation processes, and what it means for high-stakes decision domains such as healthcare, lending, or criminal justice, and how it relates to the existence of simple rate accurate models. So it is based on two papers. And let me start from the first point, where we will talk about set of good models. And if you have any questions during as I go, please feel free to ask them or send them in a chat. And if that's okay, I will just ask somebody to interrupt me and I will answer them. So in 1950, Akiva Kurosawa made a movie Rashomon, and it revolved around 4 characters. They relived the same tragic event, and then later they were asked in court what actually happened. And all of them gave very different, even contradictory statements. And the same is true with, the same happened for Leo Brayman. So he was experimenting with different regression models, linear regression models. And he said, if I try this model with this coefficient and this model with this coefficient, they achieve approximately the same error rate, but they have different parameterizations, they have different vectors and different decision boundaries. So this had to be known in the machine learning as Rashomon effect of model multiplicity. And basically, if you think about this existence of multiple models or multiple decision boundaries that achieve approximately the same error rate, it kind of changes how we view machine learning problems. So, for example, it raises questions such as, which model do I need to choose? Or what variables are important? There are so many models. What if one model has one properties, another model has another properties? Then if I do standard log analysis, leave one covariate out with respect to one model, will those covariates be still important for another model? Are we explaining the correct model in the Rashomon set? Maybe we actually explaining some nearby model of it. Is there a model that incorporates multiple objectives, for example, fairness or monotonicity, or both of them? And basically, it's kind of like an interesting phenomenon that changes our perspective, because suddenly we have multiple models that, given your objective and given what your goal is, you can take it to your benefit. But also, if you don't, I still believe you need to be aware of that risk and benefits. The question I'm actually interested in asking with respect to this model multiplicity is there a simple yet accurate model? And with respect to this question, we will cover 4 specific points. We talk about when does this model exist. We'll try somehow to quantify the Rashomon effect and see why does it occur and how often does it occur actually in practice. So let me start with trying to quantify it a little bit, and I will define a Rashomon set. To define a Rashomon set, I will take a risk. In this case, this is empirical risk, but it can be also true risk, as we will see a little bit later. So I take my empirical risk, and I take best model in class based on the empirical risk. And I will consider all models below this threshold that is formed with empirical risk of best model in class, plus some parameter theta. And I call this Rashomon parameter. It essentially allows you a little bit of flexibility, how big or small you're willing to sacrifice in order to gain more models. So it can be like 0.5% of the loss, or 1%, or it can be essentially zero. A lot of data sets allow having a lot of models that perform equally well, even with zero Rashomon parameter. And all models that are below this threshold will form the Rashomon set. Basically, it's models with loss less than some specific threshold defined by the best model in class. Now, we talked a little bit about simple models, and here is the assumption I'm going to make. I'm going to say, let the yellow be my hypothesis space. So it will be my all models that I work with. And then I will look at simple models as some models embedded in this hypothesis space. And let me give you a specific example. Let my hypothesis space, yellow, will allow different trees up to full depths, yet my blue space will be sparser trees, meaning that they are more pruned and not that fully grown. And in a way, the simpler space can form a cover over the whole hypothesis space. For example, given trees are known as a universal function approximator, so it works for them well. Now, let's bring back our Rashomon set, and we already see that if these simple models can cover this hypothesis space quite well, there is this green blob that already contains a lot of simple models. So let me try to formalize it a little bit. And this formalization, it depends on properties of specific hypothesis spaces. But let me assume that I'm given two hypothesis spaces. One is more complex and one is more simple. And I'm going to assume approximation assumption. So as long as for every model in more complex, there exists a model in more simple, such that their distance delta nearby, then the Rashomon set will contain at least a packing number of simple balls, where a packing number is a number of disjoint balls that can fit that space. And that number of balls is this size delta, exactly the same size. Meaning that if I know that for every white model here, there is a blue simple model nearby, then my Rashomon set contains at least 5 models in this case. Interestingly, this depends on the properties of hypothesis spaces. For example, it works well for trees. For some other hypothesis spaces, this approximating assumption may not hold. And we will see a little bit later that in that case, if the true Rashomon set has some properties, we can still say something interesting. But so far, what we can see from this perspective is that if the Rashomon set is large, it is more likely to contain accurate models from a simple class. So it seems like this existence of simple yet accurate models has something to do with the size of the Rashomon set. And logically, it seems to be true as well. The larger it is, the more likely it is to contain models with specific properties. And in fact, if I look back at that HIV data set, so the number of trees in the Rashomon set was 200,000, which is enormous. So no wonder I was able to find this one specific sparse, well-performing model. I kind of spoiled a little bit that we will talk about true Rashomon sets. And I think overall it is very important to be aware of the Rashomon effect. But even before this whole theory existed, a lot of researchers were able to find sparse model and see that they perform quite well. And I believe that looking into this true Rashomon set gives an intuition why this happened. So true Rashomon set is exactly the same as the Rashomon set we considered before. It's just we changed the risk. And now instead of empirical risk, I'm going to look at the true risk. But the same is true. I'm going to look at all those models such that are below the best risk in class, plus my Rashomon parameter theta. So meaning all the models that are below some threshold. Let me bring my simple models back. So as before, they are embedded in my true hypothesis, in my hypothesis space. I will make a little bit different assumption. This time I will assume that true Rashomon set contains at least one simple model, meaning that this purple blob has at least one light blue model. I don't need to know which one. I don't need to find it. I just need to know that it somehow exists in this true Rashomon set. Then what happens is that we can optimize for simpler class, for the blue class, yet enjoying good generalization benefits of the more complex class, of the yellow class. More specifically, if I look at the loss of my simple model, of empirical risk of my simple model, and the true loss of my true model, they will be somewhere nearby. Let me quantify that a little bit more with generalization bound. So as before, I'm going to look at empirical risk of my empirical risk minimizer of a simple class, highlighted in blue. And I'm going to look at the true risk of my true model, highlighted in yellow. And now we can see that it's bounded from both sides. On one hand, I have complexity terms that comes from standard generalization bounds. However, the big difference is that this complexity terms depends on a simpler class, not complex hypothesis space, meaning it is tighter than standard generalization bound. And now on this side, I have my Rashomon parameter and complexity terms that depends only on number of points and my epsilons that comes from Hofstad's inequality. So meaning that if this happened, if my assumption was true and this true Rashomon set was large enough to permit one simple model, I can optimize for my simple space and enjoy generalization benefits of more complex hypothesis space. And it's been known actually for quite a while, since 90s, that this might happen. And it was observed that very often simple classification rule models perform really well for a lot of common tabular data sets. And now we know why with this Rashomon set theory. And putting together these two arguments, we have this statement that if the Rashomon set is large enough to either permit one model from a simpler class, either hypothesis space have good generalization guarantees, it is more likely to contain accurate models from a simpler class that generalizes well. Which gives us also answer to the first question that we pose, which was when does simpler yet accurate model exist? And one of the reasons when is like when you can have large Rashomon set. Let me pause here for a moment to see if there are any questions. Okay, good. So let us continue then to trying to quantify the Rashomon set. And I will do that through the Rashomon ratio. More specifically, I will look at my whole hypothesis space, which will be my yellow blob as before, and my Rashomon set, which will be my green blob as before. And then I will simply take a ratio of these two, the volume of the green blob to the volume of the yellow blob. Interestingly, this Rashomon ratio becomes a simplicity measure of a learning problem. It kind of is an interesting statement, but let me look at it from this perspective. If the green blob is very, very small, it might be harder to find this model here. depending on the algorithm, of course. But if the green blob becomes larger, let's say I took it to extreme, in this case, it's like half of my hypothesis space, suddenly, even with simple sampling of few models, with high likelihood, at least one of them is in this green blob. Meaning the larger Rashomon set is in my hypothesis space, or the smaller hypothesis space is for this specific Rashomon set, my Rashomon ratio increases, though my machine learning problem kind of becomes simpler. Interestingly, as a simplicity measure, it's different from other complexity measures, such as VC dimensions, geometric margins, Rademacher complexity, and algorithmic stability. It's different due to different reasons, and I use illustrations to show that. So for example, for VC dimensions are data independent. For geometric margins, it's measured with respect to one model. It doesn't take multiplicity into account. Rademacher complexity measures random charges in targets, and at least for 0-1 loss, Rashomon sets are very much dependent on that. And in algorithmic stability, you can design a case where the opposite is true, whereas the Rashomon set would be independent for each regression of the targets, and algorithmic stability will be. So basically, in a way, this Rashomon ratio describes the problem of machine learning from a different perspective. Besides Rashomon ratio, other metrics have been proposed, such as pattern Rashomon ratio, pattern discovery, pattern diversity, and some followed-up work of mine also propose enumerating all models of the Rashomon set, so basically computing the volume as if how many models are in the Rashomon set, Rashomon capacity, ambiguity, and discrepancy. So we can use any of these metrics. I will describe Rashomon set from different perspectives. However, for the next experiment, I will use Rashomon ratio. And what I will do, I will try to understand how it relates to existence of simpler yet accurate model. So I will do an experiment where I will take a lot of classification data sets. And I will then measure Rashomon ratio given some hypothesis space. So I chose a hypothesis space of decision trees of depth 7, hoping it will be complex enough to incorporate a lot of models. And also I chose different algorithms such as decision trees, gradient boosting trees, random forest, linear models, and SVM. And I looked at their train and test performance, cross-validated train and test performance over multiple splits of my training data. So I will show mean, and variance will not be represented here. And interestingly, if I take all algorithms, and then I take my Rashomon ratio and sort by my Rashomon ratio going from largest to smallest, an interesting picture occurs. Turns out that all of these algorithms achieve approximately the same performance in terms of both train and test accuracy. And let me take top 12 data sets and show them to you on blob, but you will see that all of them will have approximately the same picture, and here it is. So for different data sets, my train and test performance are similar, and they're also equal. This kind of like leads us to this indirect indicator of thinking like, can we find accurate and simple model in the Rashomon set? So one of that indicator is, let me just take different machine learning algorithms and run them, and if they perform similarly, maybe there is also this optimized sparse model in the Rashomon set that performs similarly to them. And doesn't this image remind you something? We kind of like started from this goal in mind to show that on the plot of simplicity, interpretability, and accuracy, there exists this optimized sparse model, and we already get in there, where we see if this, due to this indirect indicator, we are able to, it is very likely that we can also find this sparse optimal model in there. This also answers our next question, which was, can we quantify Rashomon effect? Well, yes, we can do it through Rashomon ratio, and it also is a simplicity measure. And given this experiment where we took 50 multiple different data sets, it seemed to be that Rashomon effect occurs often in practice due to that. But we are not quite sure. It's kind of like still a 50 data set is a small representation of the whole world. So let's think about the next question, which is like, how often does it occur and why actually does it occur? And going back to that image that I have, I would like to draw your attention to kind of like two types of data sets that I had here. One of them were really accurate and had the same performance. And in a way, you can think about this data set as having really good representation. But another type of data set, they kind of like had smaller accuracy. And it seemed like they're coming from noisy data generation processes. And different algorithms still perform the same, but they had way lower accuracy than those more well-represented data sets. And this actually corresponds to what I often see in practice. If you have really huge margin, then you'll have a lot of decision boundaries between two classes and being able to fit all those kinds of different functions in between, decision boundaries in between. But also, if you have a lot of inherent noise in your data set, suddenly you'll have also a lot of decision boundaries that can classify different samples differently. And this is the next point that I would like to focus on. I would like to talk a little bit more about noise in data generation processes. And before that, there are two types of data sets that we can think about. One of them is high-stakes decision domains and tabular data sets that I typically cover in this talk, such as healthcare, lending, and criminal justice. There is also another set of data sets, which is vision and purely predictive tasks. And if we think about deep learning was able to revolutionize vision in purely predictive task area. Now it's like on ImageNet, the best performance is 95 test accuracy with 86 million parameters. I think we could just dream about this like 10 years ago. It would be unimaginable back then. But now we achieve this this really good performance. However, deep learning was not able to do such a breakthrough in high-stakes decision domains and tabular data sets. And I believe we know the reason why. And it has to do with this uncertainty of the outcomes with respect to the input. So for vision and purely predictive tasks, outcomes are a bit more certain. So for example, questions that I could ask about, for example, does this image contain a dog? Or does this image contain a toy? They are quite deterministic, they are quite specific. But questions that are interesting asking in high-stakes decision domains, for example, will this person get a diabetes in 2 years? Or will this person commit a crime in 2 years after being released on parole? They are way more complex. They have to do with non-deterministic human behavior and with a lot of random processes of the world. Maybe I'll get a job next week. Maybe I lose a job next week. Maybe I gain some weight or change my diet. All of this can lead to many different outcomes, which makes our outcomes way more uncertain with respect to the inputs as we observe in our data sets. So based on this observation, I would like to form a path. It will consist of 4 steps, and it will start with noise, with this uncertainty in our data sets, data generation processes, and it's going to end up with existence of accurate yet simple or interpretable models. And as you may have noticed, for me, simplicity and interpretability go hand in hand, because simplicity, which I typically use as sparsity, if it's sparse enough, it becomes interpretable very often. Alongside this path, I will illustrate some points with a data set, and I will use Compass data set from criminal justice domain. So in the first step of this path, what actually happens as you have more uncertainty of the outcomes is that variance of the loss increases. To see it more specifically, let me plot the hypothesis space on my x-axis and my risk on my y-axis. And this is, for example, how it may look like, how my variance may look like for some non-noisy data set. However, if my data set comes from noisy data generation process, or I can model that by adding more noise to the data set, suddenly the variance of the loss keep increasing. So I ended up in this uncertainty cloud where everything is more like cloudy and foggy. And I have formally proved this for different noise models. So for random label noise with some probability, for label noise where my probability of flipping my label depends on my axon, actually on my input, and it helps to model for different protected groups or for some other purposes that might be in mind, for margin noise that occurs from moving Gaussians, and for additive attribute noise. So let me look at more specifically at 2 cases. So for example, for uniform random label noise, where I flip each label with some fixed probability, here is a plot based on Compass dataset, where on x-axis I have my uniform label noise as I keep adding it to the dataset to help to model for different data generation processes. And on y-axis, I have my variance of the loss. And I can see that with more noise, my variance of the loss increases. And this is true in general. So for 0, 1 loss, if I take a fixed model F and consider two different probabilities with which I will flip my labels P1 and P2 and form data sets based on that. So the variance over this fixed model F and true distribution will be lower than the variance over this fixed model F and true distribution for P2. So here I have P1 and here I have P2. So my variance strictly increases. The same is true for margin noise. And what do I mean by margin noise? It kind of sounded a little bit mysterious. So let's say that we take two Gaussians, and let's say they are like far away apart. And now I move them closer together. As I move them closer together, I introduce more uncertainty near the decision boundary. That's why I called it margin noise. So for example, on this plot, I have my one Gaussian, blue Gaussian, and my red Gaussian, and I will be just moving them closer to the center. And suddenly they are overlapping, so there is way more uncertainty in the middle now. So it turns out that for balanced data sets, it comes from Gaussian distribution, and I will consider hypothesis space of linear models. I can formally show that as I move these two Gaussians closer together, or in this case, I kind of like multiply the means of the Gaussian, then as they become closer, the variance also increases. And here is an illustration where I have my margin noise, how much I move them closer on y-axis, and I have variance of the loss on, on x-axis, and I have variance of the loss on y-axis. And I consider Gaussians in different dimensions. And for all of them, variance of the loss keep increasing. Okay, great. So hopefully this is convincing enough that for different type of noise models and for different noise models, we have increase in variance of the loss. So it turns out when this happens, actually generalization error also increases. So let me show it a little bit more formally. I'm gonna look into true risk and empirical risk, and I'm gonna use Bernstein inequality in order to bound that. And that's how variance occurs in this bound. So now I have my complexity of the Rashomon set, and I have variance of the loss here. As my variance increases, this upper bound in my generalization performance also increases. And I can also illustrate this based on the COMPASS data sets that we discussed. So let me actually take a very simple algorithm, which would be CART, and let me fix the tree depths. I will allow the tree to be changed, like as best as fitted to data, but the depth of the tree will be fixed. And now as I have more noise in my data generation processes, which is modeled on my x-axis, turns out the train and validation accuracy will keep increasing. The train minus validation accuracy, the difference will keep increasing, meaning that my generalization gap will only grow as variance of the loss increases. Interestingly, but if I'm like a data scientist, seeing this process and modeling for it, I'm kind of realizing that this is happening. So the next step, what will happen, I will have to reduce the complexity of the hypothesis space in order to compensate for it, in order to compensate for the increase in train minus validation difference, the generalization error. And this is quite logical step, but let me also illustrate it based on the cross-validation process on COMPASS dataset. So now instead of fixing the depth of the tree, I will say, I allow you to be anything from depth 1 to depth how much you want. And I will use cross-validation in each step to choose the best depths. And what actually then happens as I plot my label noise on x-axis and best depths of the tree on y-axis, with more noise, the depth of the tree that cross-validation chooses actually decreases. And this experiment intended to model the data scientist who works on this problem and try to choose the best hypothesis space. So it kind of gives us an intuition that if we come from more noisy data generation processes, we will prefer shorter decision trees in this case, or simpler hypothesis spaces. Interestingly, we already are in a simpler hypothesis space. So we started with depth 7, we ended up with depth almost 4 here. So we kind of like already got to this last point that we wanted to. But here is one more step that is left. And I would like to connect this step to the first part of the talk that we talked about, which was Rashomon sets and Rashomon effect. Well, it turns out that as you decrease complexity of your hypothesis space, for simpler hypothesis spaces, actually Rashomon ratio is larger. And I have formally proven this for hypothesis space of fully grown decision trees. And in this case, we can show that as you have decision trees of depth 10 and decision trees of depth 9, that these hypothesis spaces will have like larger Rashomon ratio of smaller depth decision trees. But also what I would like to focus a little bit more, I also shown it for linear models in case of ridge regression. And this case is interesting because it kind of completes this whole path and validates it. So let's look a little bit more closer into ridge regression case. First interesting observation is that for ridge regression, we can measure the Rashomon set in a closed form. So let's take least squares loss. And here is a simple plot in 3D where we have loss on one dimension, and then we have two parameters that parameterize the linear model space. And recall that we are looking at our best performance and some threshold. So let me go and draw this threshold and look at all of models below it. Essentially, the volume of all those models will be an ellipsoid. And I can just compute the volume of that ellipsoid in order to find my Rashomon set. This is intuition for least squares. It's also true for ridge regression. The Rashomon set for ridge regression is also an ellipsoid, volume of which I can compute. So this equips me with a very nice opportunity to measure my Rashomon ratio directly. Now let's go back to my noisy data generation processes. And this is known fact that for a lot of data sets, for some losses and for some problems, depending where you inject noise. So for example, for stochastic gradient descent, noise can act as an implicit regularizer. So the same is true for ridge regression as well. So as I add additive attribute noise, meaning that for my attributes, I add some noise epsilon, such as it's sampled from my normal distribution. And for my new data set, X prime and my new data set will consist of all those examples that have my original data plus some noise. So then optimizing for my noisy data set, here as epsilon denotes this noisy data set, is the same as optimizing for my original loss plus stronger regularization optimizing over my original data set, however, with stronger regularization, meaning that this noise acts as an implicit regularizer for ridge regression. Okay, great. So we now see that we started with additive attribute noise and we ended up directly in that step 3. However, I also verified that for least squares and ridge regression, both step 1 and 2 happen theoretically. Now, interestingly, the next step for ridge regression, also Rashomon ratio over smaller amounts of noise will be smaller than the Rashomon ratio over the larger amounts of noise. So meaning that more noise, more regularization, and larger Rashomon ratio, which directly goes from my noise to my increase in the Rashomon ratio and validates this whole path. Also, I wanted to discuss a little bit what happens with 0-1 loss. And this is currently ongoing work. But what we noticed, and I thought it might be also helpful to validate this, this process, is that for 0-1 loss and models in the Rashomon set that comes from noisy data generation processes, turns out that these models tend to be simpler than models in the Rashomon set that comes from cleaner data generation processes. So it's not even a question of my optimal model, it's a question of my whole Rashomon set. So those models that come from noisy data generation process tend to be simpler. And this is like, impact of this is huge. It means that whatever model I choose, it will be more simpler than models that comes from cleaner data generation processes within my near optimal models, set of near optimal models, which also helps to validate this step of this path that consists of 4 steps. Now, interestingly, both of this case, ridge regression and 0-1 regularized loss, they are both regularized. However, what if I'm not regularizing? Let's say that I don't want to do that, and basically I'm skipping step 3, so I will not reduce the complexity of the hypothesis space. Turns out, in this case, my Rashomon ratio will still increases. And here is an illustration to help see that. So here I perform an experiment for different data sets where I keep adding my label noise, and it is depicted on my x-axis. And then I looked into the size of the Rashomon set, and it is on my y-axis. Now, because I don't regularize, it means that my hypothesis space does not changes. So denominator of the Rashomon ratio does not changes, but numerator keeps increasing, as we can see from this plot. So I have more and more trees in my Rashomon set, which also corresponds to the increase in my Rashomon ratio. Great. So we start with this uncertainty of the outcomes with respect to the inputs, and we ended up with existence of simple yet accurate models and increase in the Rashomon ratio. And I would like to reinforce that it especially works for high-stakes decision domains that typically corresponds to noisy data generation processes. And in these domains, we can find these more specific sparse interpretable models. It also gives us answers to the last question when we asked, why does the Rashomon effect occur? And one of the reasons is noise. But also now we can see that it occurs in practice more often than my limited experiment with 50 data set could allow me to do, because I would expect it occurs for a lot of high-stakes decision domains. Another interesting question is how much noise, like, is there like some quantification of how much noise does need to be for me to consider simple models? And we are working on that, but also I wanted to have this point that it doesn't have to be like, we don't necessarily need to know how much noise is present. Essentially, as long as some amount of inherent noise is present, we should consider regularizing for better generalization. On the opposite, and there has been work that shows this, if you expect no inherent noise at all, you can consider more complex models. In fact, as complex model as you like, it will still generalize in that case. So as long as practitioners suspect some amount of noise, I would encourage them to follow this path. And also this path becomes this mathematical proof that for a lot of high-stakes decision domains, we can expect no simplicity-accuracy trade-off. And there are two reasons why I'm very excited about this proof. So first, it's kind of like a nice phenomenon that occurs in practice that now we are able to explain a little bit more, why for so many datasets we can find these sparse good models. But also it leads to technical justification for why interpretable models should be default for a lot of domains. And on that, I would like to thank you very much for the attention.
Yeah, thank you. Thank you very much. I see everyone applauding in the chat. I'll stop the recording now and we can discuss a bit.